Welcome to Statistical Computing. Today, we are diving into a fundamental and incredibly powerful concept in C and C++ programming, function prototypes and calls. Whether you are writing a simple script or building a massive software project, understanding this topic will completely transform how you organize, structure, and write your code. It is the key to making your programs modular and professional. Let us get started on this journey. To begin, imagine organizing a large event. Before it starts, your caterer gives you a summary sheet of what they will provide and what they need. In programming, this is exactly what a function prototype is. It is a brief message to the compiler, declaring the function's name, its required inputs, and its output type before it is actually used. Without this rulebook, the compiler would panic when it sees a new function. A function call, on the other hand, is the actual moment you hand over the ingredients and trigger the function to do its job. Now that we understand what a prototype is, let us look at its mathematical equivalent. In mathematics, we define a function's mapping before using it. Here, f represents the name of the function. The symbol x represents the domain, which is the set of all acceptable input values. The symbol y represents the codomain, or the possible output values. In C and C++, the prototype explicitly tells the compiler what sets of data go in as arguments and what comes out as the return value. If you pass an input outside the domain X, the compiler throws an error. Let us visualize this mapping to make it completely clear. On the screen, you see two distinct sets. The oval on the left represents our domain, containing our input arguments like x and y. The oval on the right is the codomain, representing the return type, containing our output z. The arrow connecting them is our function f. This diagram perfectly illustrates what a function prototype does. It establishes the strict pathway between the specific inputs you provide and the specific output the function guarantees to return. This strict rulebook we just saw leads us to an interesting shortcut. What if we do not want to write a separate prototype? If you write the complete, full definition of the function above your main program block, you can skip the prototype entirely. Because the compiler reads your code from top to bottom, it encounters the full function first and automatically learns its signature. By the time it reaches the function call in main, it already knows the rules. This saves typing in small programs, but for massive software projects, separate prototypes are necessary to keep code organized. Moving beyond standard C, let us explore a powerful feature exclusive to C++ called default arguments. A default argument is a fallback value specified right in the function prototype. Imagine ordering a coffee. If you do not specify the sugar, the barista adds 1 spoon by default. Similarly, if a programmer forgets or chooses not to provide a specific input during a function call, the compiler automatically uses this fallback value. This makes your functions incredibly flexible and significantly reduces repetitive coding. Let us see how default arguments work with a concrete mathematical formula. This equation calculates the total cost of an item. T represents the total cost, P represents the base price, and R represents the tax rate as a decimal. In C++, we can write a prototype where the tax rate R has a default value, like 0.05. If you call the function and only provide the base price P, the compiler automatically fills in 0.05 for R. If you provide both, your new tax rate overrides the default. Another major feature unique to C++ is function overloading. In standard C, every single function must have a completely unique name, which gets frustrating. Overloading allows you to create multiple functions that share the exact same name. The only strict requirement is that their parameter lists, meaning the number or types of their inputs, must be different. The compiler acts like a smart traffic cop. It looks at the arguments you provide during the function call and automatically directs the data to the correct version of the function. To understand how the compiler acts as a traffic cop, let us look at mathematical notation. In math, we usually give different subscript names, like G1, to distinguish functions. This first formula takes exactly one input, x, and squares it. In C++ function overloading, we drop the subscript and simply name this function g. When you make a function call and pass exactly one argument, the compiler counts the inputs, matches them to this specific rule, and executes this squaring operation. Now, suppose we have a second formula that takes two inputs, x and y, and sums their squares. In math, we might call this g2. But in C++, we can also name this function g, sharing the exact same name as the first one. When you make a function call and pass two arguments instead of one, the compiler automatically ignores the first function and executes this one instead. It directs the data to the correct formula based purely on how many inputs you provided. Now that we understand these features, let us see this with a concrete example. We need to write a program that calculates the area of a rectangular plot of land using a custom function. This is a very common task in geometry and computer graphics. By breaking this down, we will see exactly how the prototype, the function call, and the mathematical formula all connect together, and how data flows seamlessly from the main program into the function. We begin by defining the mathematical formula for the area of a rectangle. In this equation, A stands for the area, L stands for the length, and W stands for the width. To implement this in C, we write a prototype that declares a function returning a decimal value, taking two decimal inputs for L and W. This sets up the strict rulebook. Now, let us see what happens when we actually call this function with real numbers. When we write the function call in our main program, we pass actual numbers. Here, we provide 5.0 for the length and 3.0 for the width. The program pauses its current task, jumps to the function, and substitutes these real values into our formula. The function multiplies 5.0 and 3.0 together. Finally, it returns the calculated area of 15.0 back to the main program. This shows the exact moment the function does its job. Let us look at a second example that perfectly demonstrates function overloading. Suppose we need to calculate the statistical mean of a dataset, but our input data comes in two different formats. Sometimes we have the total sum and the count of items, and other times we just have two specific numbers we want to average. We need a flexible system that handles both without confusing the user. We will use C++ function overloading to handle both scenarios using the exact same function name. For our first scenario, we define this mathematical formula. Here, mu represents the statistical mean, S represents the total sum of all values, and N represents the total number of items. We write a C++ prototype that takes a decimal for S and an integer for N. If we call the function and provide a decimal and an integer, the compiler knows to use this specific division formula. This ensures the correct mathematical operation is applied to these specific data types. In our second scenario, M is the mean of just two specific numbers, A and B. We write a second prototype with the exact same name as the first one, but this time it takes two decimal numbers as inputs. If we call the function and pass two decimal numbers, the compiler automatically ignores the first formula and uses this one instead, adding the numbers and dividing by 2. The compiler successfully directs the data based purely on the input types provided. We have covered a lot of ground today. Remember, function prototypes are the absolute backbone of modular programming, establishing the rules before a function is ever used. A function call is the actual execution using specific data. We also saw how C++ features like default arguments and function overloading make your code incredibly flexible and clean, allowing teams to work efficiently. You now have a solid understanding of how data flows through functions. Great job!